Millikan's oil drop was used to determine the charge on an electron. In this experiment, there were two horizontal plates, and a charged oil drop was inside the plate. In the first condition, the oil was allowed to fall vertically downward under the action of gravity. So during that time, what forces we will consider that the oil was falling downward due to the force of gravity mg, and at the same time an upward force is also considered to be acting on the drop in upward direction. The force is viscous force F, as well as upthrust. Upthrust and viscous force are acting in upward direction, and weight of the oil drop is acting in downward direction. So under equilibrium, when the drop will attain its terminal velocity, during that time the total downward force will be equal to the total upward force F plus U. F is the viscous force. Formula is 6 pi eta r v, where r is the velocity of r is the radius of the drop, v is the velocity of the drop, terminal velocity of the drop, and similarly upthrust is b rho g, where rho is the density of the medium. We consider here the density of the medium as sigma, and g. If the radius of the drop is r, then volume can be written as 4 by 3 pi r cube, since it is of a spherical shape. Similarly, mass can be written as density of the drop into volume into z, and volume again 4 by 3 pi r cube density g. Here in the above, in this expression, rho is the density of the oil drop, and sigma is the density of the medium, that is air, and v is the velocity of the oil drop. We can solve this to obtain the radius of the oil drop as r is equal to root under 9 eta v by 2 rho minus sigma into g. This was the first case. Now in second case, we will apply electric field between the plates. Electric field E is applied between horizontal plates. In the first case, electric field was absent, that is, electric field was not applied between the plates, and during that time only three forces were acting: weight mg in downward direction, upthrust, and viscous force in upward direction. But in the second case, the situation is a bit different. Now here we will consider the electric field between the two plates. In that case, the total forces on the charged particle will be mg, its weight, electric force in upward direction QE, charge into electric field, upthrust in upward direction, and viscous force will depend on the direction of the charged particle. If the charged particle is moving down, the viscous force is upward. If the charged particle is moving up, the viscous force is downward. So here we consider charged particle moving upward. In that case, viscous force will be opposite to the motion downward. So at equilibrium, when the charged particle will attain terminal velocity, at that time the total upward force will be equal to total downward force. Now the upthrust is 4 by 3 pi r cube. Density of the medium into G is equal to 4 by 3 pi r cube. Density of the material or oil into G plus upthrust. Upthrust is 6 pi eta r V. For the second case, we consider the terminal velocity as B dash. So this becomes QE plus QE is equal to 4 by 3 pi r cube sigma minus rho minus sigma into G plus 6 pi eta r B dash. Side can be obtained from asterisk. QE is equal to 6 pi eta r B plus 6 pi eta r B dash. This gives QE is equal to 6 pi eta r B plus B dash. Finally, the charge on the oil drop is equal to 6 pi eta r by E into B plus B dash. This is the equation if the charged particle in the presence of electric field will move upward. Similarly, if the charged particle in presence of electric field is moving downward, then our formula will be Q is equal to 6 pi eta r E V1 minus B dash. So we have three formulas over here. One for the radius of the charged oil drop, and another two formulas for the charge on the oil drop, equation 2 and equation 3 for two different cases. The equation 2 is for charge moving upward in electric field, and equation 2 is for charge moving downward for presence of electric field. And another important thing we need to consider, V is the velocity in absence of electric field. B dash is the velocity in presence of electric field. Okay, we have first question related to the above topic we discussed. In Millikan's apparatus, an oil drop of weight 2 into 10 power minus 15 kg acquires 2 surplus electron. When a PD of 620 volt is applied between the pair of horizontal metallic plates, the drop is in equilibrium. Find the distance between the plates. So here two metal plates are considered. The potential between the two plates is 620 volt and we need to calculate the distance. The oil drop has charge Q is equal to 2 electron, that is 3.2 into 10 power minus 19 coulomb, and mass of the electron is 2 into 10 power minus 15 kg, and nothing more is here given to be considered. So we will here consider only two forces, one its weight mg in downward direction and another its electric force in upward direction. So at equilibrium, the two forces are considered to be equal, that is QE is equal to mg. So from here we can calculate the electric field. 3.2 into 10 power minus 19 into E is equal to 2 into 10 power minus 15 into 10. This gives the value of E as 62500 volt per meter. Again we know that electric field E is given by V by D. So 62500 is equal to provided voltage is 620 by T. Therefore, T is calculated as 9.9 into 92 into 10 power minus 3 meter, that is 9.92 mm is the required answer. We have the next question. In a Millikan's oil drop experiment, a charged oil drop of density 900 kg per meter cube is held stationary between two parallel plates 9 mm apart, held at a potential difference of 150 volt. The two parallel plates are 9 mm apart and the potential difference between the two plates is 150 volt. So electric field between the two plates is V by D is equal to 150 by 9 into 10 power minus 3. This gives to be 16666.67 volt per meter. And when the electric field is applied, the oil drop is stationary, and we know that in presence of electric field, terminal velocity is denoted by V dash, and in the question it is written that the charged oil drop is at rest, so V dash is equal to 0, stationary. When the electric field is switched off, the drop is observed to fall steadily a distance of 3 mm in 53.5 seconds. That means in absence of electric field, the velocity v is given by distance by time, that is 3 into 10 power minus 3 meter divided by time 53.5 seconds. This gives to be 5.607 into 10 power minus 5 meter per second. Now we need to calculate the radius is equal to what and charge is equal to what. We have the direct formula for radius as r is equal to root under 9 eta v by 2 rho minus sigma into g. Rho is the density of the oil which is given, sigma is the density of air, and the density of air is 1.29 kg per meter cube. Similarly, eta is the viscosity of air, this is 1.80 into 10 power minus 5 Newton second per meter square. Generally these values are provided in the question, so we will put these values and calculate the result. .18 into 10 power minus 7 meter. Similarly, the charge on the top can be calculated by using the formula 6 by eta r by e v plus v dash. 6 into 3.1415 into 1.8 into 10 power minus 5 into radius is calculated as 7.18 into 10 power minus 7 by electric field 16666.67 into 5.607 into 10 power minus 5 v plus v dash 0. 8.195 into 10 power minus 19 coulomb is the required answer. Next question is, an oil drop of mass 3 into 10 power minus 11 gram, 3 into 10 power minus 11 gram, and radius 2 into 10 power minus 4 cm carries a 10 axis electron. it moves upward with a terminal velocity of 2.7 into 10 power 2.7 into 10 power minus 4 meter per second in an electric field. So this is b dash. In presence of electric field, what is the magnitude and direction of electric field? And viscosity of the air is given as 180 into 10 power minus 7 newton second per meter square, and the buoyant force of air is neglected, that is 0. Density of air is considered to be 0. First we will convert all these values into SI unit. Minus 19, that is 1.6 into 10 power minus 18 coulomb. So here since air force is buoyant force of air is neglected, the forces acting on the charged particle in presence of electric field are its weight mg, electric force QE, and upthrust U. Upthrust is neglected because buoyant force of air is neglected, so only the force another force acting here is viscous force F, and it is directed downward as the charge is moving upward. So our equilibrium equation will be QE is equal to mg plus F. QE is equal to mg plus 6 pi eta r b dash. 18E is equal to 3 into 10 power minus 14 into 10 plus 6 into 3.1415 into 180 into 10 power minus 7 into radius 2 into 10 power 6 into velocity 2.7 into 10 power minus 4. Putting all this value, we obtain the value of E as 3.02 into 10 power 5 volt per meter, which is the required answer. Okay, now we have another question. An oil drop of mass 3.25 into 10 power minus 15 kg falls vertically with a uniform velocity through the air between vertical parallel plates. Here the plates are vertical, which are 2 cm apart. When a potential difference of 1000 volt is applied to the plates, the drop moves to the negatively charged plates, its path being inclined at 45 degree to the vertical. Calculate the charge on the drop. Okay, now here this is the oil drop, and in absence of electric field the oil drop will fall downward. When electric field is applied, the charged oil drop is attracted towards positive charge with a force of QE, and the resultant of the two forces QE and mg will make angle 45 degree with the vertical or horizontal. Any case, both the angles are same. 45 degree. So here we can write as tan theta is equal to vertical force by horizontal force, and tan 45 is equal to 3.25 into 10 power minus 15 into 10 by charge is needed to be calculated. Electric field, we can calculate electric field as B by D is equal to 1000 by 0.02, that is 50,000 volt per meter. So here electric field is 50,000 or Q into 50,000 is equal to 32.5 into 10 power minus 15. Therefore Q is equal to 6.5 into 10 power minus 16 coulomb. Sorry, 10 power minus 19 coulomb. This is the required answer.